So we were partway through proving Lagrange's theorem. Oh, it's there. The stage we've got to is we've described how we can take a group, given any subgroup, which we can think of as a subset of the elements, contains at least the identity. It's an interesting subgroup, contains some other elements. And by using the coset construction, this gives us a system of other subsets of G, which we've now proved that they partition G. We have these other left cosets, AH, BH, CH, DH, FH. Okay? This other system of cosets. Okay? So we have proved that the collection of cosets, the collection of left cosets, partitions G. Meaning every element of G is in one of the cosets. Specifically, an element X is in the coset X times H. H contains the identity, so it will contain the product X times the coset XH will contain the product X times the identity. So the coset XH contains the element X. So every element is in some coset, and cosets generated by different representatives are either exactly the same or they're disjoint. There's no partial overlaps. One coset is partial, is non-trivial intersection with another one, but yet they're not the same. Again, that can't happen. Okay, so we have these different cosets partitioning G. So obviously you can count the elements in G by counting the ones up here, adding to the amount in here, adding to the amount in here, etc. What we've yet to prove, what's going to complete the proof, is when we prove that each coset has the same number of elements. Okay. So I think we'll jump to it and prove that straight away. So this is proposition 6.9. Proposition 6.9 says that H is subgroup G, find some map. Map is about check. So this is essentially, it's proving all left cosets of H and G contain the same number of elements. Okay, that's my paraphrasing of what the statement of proposition 6.9 is in the book. Okay. He works the definition of this map into the statement of proposition 6.9. This is essentially what it's saying. So, okay, well this looks, I mean, we've got no information to go on about G, about H. How on earth are we going to prove that any two left cosets have the same number of elements? We've got nothing to deal with all this. Well, because it's so general. So we're just going to deal with what we have. And all we have is the existence of the subgroup, definition of the coset construction, and just the basic group axioms. Okay. So we do this by proving any left coset. I'll use the same notations he uses. Any left coset little g times h has the same number of elements as h. How do we do this in general? How do we prove that two? These are, of course, finite sets. Okay, in all of this, we're assuming G is a finite group. It's in the statement of Lagrange's theorem. General method for proving that two two finite sets of the same number of elements is to construct a bijection between them. You've got one set here with a bunch of elements, you've got another set here with a bunch of elements. You can demonstrate and prove that they're the same size by constructing a bijection between them, namely a one-to-one and onto mapping. Okay. A mapping, by definition, has to associate an element from in here in the codomain with everything in here. So we're kind of using up all the elements here. The fact that it's injective means we never have two elements going to the same element here. So we're never kind of undercounting over here. And a bijection is also surjective, meaning everything in here is used up. I really did draw the same number of marks. Okay. So if you set up a surjective and injective mapping between them, then you can claim that the two sets have the same number of elements. So if there exists a bijection phi, this is congenial set theory principle, a bijection phi going from x to y, then x and y have the same, x and y have the same size. If you think about it, well, what is the process? Like if I count the number of people in this room, I go 1, 2, 3, 4, 5. What I've done is set up a bijection between the set of people in this room and the numbers 1 to 5. So I've labeled you with 1, labeled you with 2, 3, 4, 5. I'm doing counting wrongly if I go 1, 1, 2, 3, 4, because then it's not injected. So I'm labeled 2 with you with 1. Also, if I count the number of people in this room by going 1, 2, 3, 4, it's 4 people in this room. It's wrong, so it wasn't surjective, so I didn't count. Okay. So that's what you're doing when you're counting things. You're setting up a bijection from the counting numbers 1, 2, 3, 4, 5, 6 to end with the elements in the set that you're counting. So that's what we're doing. So what is the phi? We need some way of mapping elements. Define phi and mapping H to GH by I don't look in the book, but this is done to the head time. What element? Not that I keep doing it to Jordan. What element do we map H to? In here. You've read the book. Yeah. But the point is there is what there's only one reasonable answer to this question. So which element do we map H to? It has to be an element of this set. G times little h, yeah? It'd be perverse to choose anything else. We don't even have anything else to hand to choose. We know about this chosen element G. We know about this chosen element H. We know of no other things to build an element in here. So it may as well be G times H. Okay? So we map an element from the subgroup H to an element in this left coset. And we map the element little h to the product little g times little h. So all we have to do is prove that phi is 1-to-1 and onto. Okay, it's injective and surjective. It's clear. I mean, there's not much to prove on the surjective front. It's clearly surjective, since GH is, by definition, just the set of all these products. G times H, where the little h comes from subgroup H. So do we see all these elements arising as values of the map phi? We can, because we can put in any of these h's as the argument, because the phi is going from subgroup H. Yeah. So certainly every element in the codomain occurs as a value. That's clearly subjective. For injectivity, well, let's assume that phi of H1 is equal to phi of H2, i.e. G of H1 equals G of H2. That's what phi is defined as being. And what conclusion do you draw from that? Cancel the G's, yeah. We're in a group, we can multiply both sides by G inverse. So that implies that H1 is equal to H2. So if two arguments have the same value under the mapping phi, they are in fact the same argument. So therefore it's injective. You never have two different elements getting mapped to the same element. So be your H1, H2, and phi of H1 equal to phi of H2. That can't happen. The only way it can happen is trivially we just label the same element as H1 and H2. So phi is bijective, 1 to 1 and onto. So the size of H is equal to the size of GH. Remember, modular signs around a subset just means the number of elements. The size of the subset. Now this is all for finite sets. So this is like a basic principle of finite set theory, that if there's a bijection between the sets, they have the same number of elements. When you extend to infinite sets, you can still talk about mappings between infinite sets. Then this doesn't become a property of infinite sets, really. This becomes the definition of when infinite sets are said to be of the same size. For infinite sets, we define them. What it means to say that two infinite sets have the same size, what that means is there is a bijection between them. So this concept here is a property of finite sets. And this is what Cantor created in the 18th century, 19th century. He created the theory of infinite sets and the sizes of infinite sets by realizing that this property of finite sets could be used as the definition for the concept of infinite sets having the same size. And this is why we speak of the natural numbers having the same size as the integers, the same size as the rationals. Even though we normally think of the integers as being embedded, a subset of the rationals, and the rationals has loads of extra elements that aren't in the integers. But nevertheless, you can define bijections between the integers and rationals. So they are regarded as having the same size. And you can prove, it's called Cantor's diagonalization argument, that there is no bijection between, say, the integers and the real numbers. So the real numbers are a genuine, bigger infinite set, larger in size than the other integers or rationals. Okay. So that would take you, if you followed it, all the way into theory of infinite sets. And it turns out there's a whole infinite hierarchy of sizes of infinite sets that are all coming from this central idea. Okay, but now we've proved Lagrange's theorem. We've basically done it with that, okay? Because this little g times h, this was any old left coset. So they all contain the same number of elements of h. So how many things are there in G? What is the size of G? Well, we've got it nicely partitioned, so we're just going to count the number of things in here, add it to the number of things in here, add it to the number of things in here. So just count the number of things in each cell, add them all up, we get the total number of things in G. Well, in each cell, we just proved in each cell of the partition here is the same number of things, namely the size of H. So we're just multiplying it by the count of the number of left cosets, the number of distinct left cosets. Number of left cosets. Okay, so that's Lagrange's theorem. So the final proof of Lagrange's theorem is just like one little sentence, really, in the book, or 2 sentences or whatever. One thing that I've skipped over, or sorry, any questions on? So it's like a really, I mean, I hesitate to use the word simple because none of these things are simple when you're seeing them for the first time, but it is like a simple idea, isn't it? Split the set up into cells. This is what when I refer to these cosets as being translates of H. Yeah, when you multiply everything on the left by A, it kind of shifts all the elements over here. If you multiply everything in H by B on the left, it kind of shifts them all over here. So you're moving the subset H around to create these different subsets that partition G, the same number of things in each subset. Therefore, the size of this has to be a divisor of the size of G. So that gives us the so yeah, do read through everything in the chapter, because there's quite a few little pieces I'm not mentioning in the lecture. There's good stuff there. There's just a piece of notation that he uses. So we refer to this thing. So square brackets G colon H. This is known as the index of H in G. And it's equal to the number of left cosets of H in G. So in the case, because we've just proved Lagrange's theorem, in the case when G is a finite group, this is simply the size of G divided by the size of H. Okay, so in finite groups, the index is just this integer, which is the ratio of G to the size of G to the size of H. Obviously, if the group G is infinite, you can't talk about this, form fractions with infinity. So then it's just the number of left cosets. Now there might be an infinite number of left cosets H and G, if G is infinite, or there might be just a finite. We should discuss some examples as well. So straight away, so Lagrange's theorem is very powerful in a way because it applies to all finite groups. So we get a number of interesting corollaries straight away. So if you look at, I don't bother writing these out, corollaries 6.11 and 6.12. So straight away now we know, suppose G is a finite group and little g is an element. Okay, now we're saying the order of G must divide the number of elements in the group G. Why is that true? Now Lagrange's theorem is about subgroups. So what are we talking about here? Remember, the order of an element is the smallest positive power of that element that brings you back to the identity. G to the power 0 is by definition the identity. Then you got G1, G to the power 1, G squared, G cubed. You're in a finite group, sooner or later you're going to come back to the identity. And that the smallest such exponent that does that is the order. Is the order of G. But it's also the size of the cyclic subgroup generated by G. So when you pluck out any element little g, that can generate a cyclic subgroup of the group, just the set of all the powers. But we've just proved that the size of any subgroup is a divisor of the size of G. Therefore, the size of the cyclic subgroup generated by little g divides the size of capital G, so therefore the order of G divides the size of capital G. Okay. If a group has prime order, group of size 23, naively, or not naive, but at the beginning, we've got, before we saw Lagrange's theorem, we've no reason to expect to know anything much about groups of size 23. There could have been a whole variety of different groups of size 23. We could have had lots of interesting structure. Could have been loads. Turns out there's really essentially just one, what we'll call later isomorphism class, but there is really only one type of group of size 23. Because if the size of the group is a prime number, well, the conclusion of this corollary is the group is cyclic. So it's a cyclic group of that size. Very easy group to understand. It has a generator, and the group just consists of the different powers of that generator. You visualize the whole thing as a cycle, as a circuit. The identity to G squared to G cubed, all the way back to the identity. It's a very simple ring structure. And the reason of that is because if we take, so if G is a prime number, if the size of G is a prime number, so it's a number at least of size 2, so the group certainly has a non-identity element. So the group of size at least 2, it's going to be a non-identity element. But then the previous corollary just says, well, the order of that element divides the order of the group. If the order of group is prime, there's only 2 things that divide it. One itself, P. But the only element that has order 1 is the identity itself. So if we choose a non-identity element with a G, its order must divide P, so therefore its order must be P. It can't be bigger than P. It must be P itself. So that means the cyclic subgroup generated by that element, subgroup of G, it has size P. Therefore, it must be all of G. And G is the cyclic subgroup generated by any one of its non-identity elements. Okay. So a group of size 23, that's fine. I know it must be equivalent to the cyclic subgroup generated by an element of order 23. There's no other types of group of size 23. Does that make sense? So that's an example of a very powerful type of result where just knowing the size of the group means essentially you know everything there is to know about it. Obviously, when the size of the group is not prime, this kind of argument doesn't work. So groups which have size not prime, they can have complex structure. And there's more variety in it. And some of the later results in the unit are all about what you can deduce about the group based on knowing the size of the group. This is a very strong result in that just knowing that the size of the group is prime means you know an awful lot about it. It's cyclic. But some other results will be saying, well, if you know the order has got 2 or 3 prime factors or something, we'll be able to make deductions about this, about the group, about what subgroups it has. Okay. So there's corollary. There's a little bit of corollary about things with the index there. Section 6.3 applies this thing to the multiplicative group of congruence classes and talks about the Euler phi function. So you all know everything about the Euler phi function because you did number 3 last year. Okay? So the things in section 6.3 will be familiar facts to you from last year's number 3. But he's establishing them or arriving at them via group theory, via Lagrange's theorem. Okay, applied to the group, the multiplicative group of congruence classes modular n. So you'll remember Euler's theorem, you'll remember Fermat's little theorem from last year. Okay, so we can arrive at those via Lagrange's theorem. I think last year we proved them directly, using not talking about groups much, just talking about divisibility and prime numbers and properties of integer modular n. Whereas here he kind of arrives at them from above by using Lagrange's theorem. So I'll leave you to any questions of the now, what's left there is remark 6.14. So this is important. So think again what Lagrange's theorem says. It says if the size of the group is finite, right? The size of the group is finite. The possible sizes of subgroups is restricted to the divisors of the size of the group. Okay? That's what Lagrange's theorem says. So this raises the question of what's commonly known as the converse of Lagrange's theorem. So I laid this out yesterday in the introduction, but this says, so if the size of G is n and D divides n, must G have a subgroup of size D? Question. Lagrange's theorem says the only possible subgroups you might observe, they'll always have size D where D is subdivisor of n. Okay. So Lagrange's theorem tells you about subgroups that don't exist. It says, like in a group of size 15, there won't be a subgroup of size 4. There won't be a subgroup of size 8. It says there might be a subgroup of size 3. There may be a subgroup of size 9. It doesn't assert that there is. You've got to be clear on that. Whereas this is raising that question, is there a subgroup of this size? Of the size D where D divides n? Well, the answer to this is not necessarily. In certain groups, a lot of the time, well, there are results known of this nature, which are called the Seelof theorems, which you'll be meeting at the end of the course. But in the answer to this general question is no. So must G have a subgroup size D? Well, the answer is no. Not necessarily. So, okay, we need an example to show that. Okay. So the example, the standard counterexample to this. Well, standard counterexample, I think it's the easiest counterexample, so the smallest counterexample, the first counterexample we can show this is we consider A4. Okay, so this is the one which is laid out in 614. What's A4? A4 is known as the alternating group. So Jan was telling you about these permutation groups. Alternating group on 4 symbols. By definition, it's the set of all permutations sigma from S4. S4 is the symmetric group. Index 4, the group of all permutations of 4 objects. The alternating group is the one where consisting of all the even permutations. Yeah? All the even permutations. The ones which can be expressed as a product of an even number of transpositions. Okay. S4 has size 4 factorial, which I believe is 34. The alternating group always has size of half of the enclosing S4 Sn. So the size of A4 is 12, half of 4 factorial. And 6. Sorry.
I was just saying about the factors of 12.
Factors of 12. Yeah.
1, 2, 3, 4, and 6.
1, 2, 3, 4, and 6. So.
Well, on 12, obviously, yeah. So.
Yeah. Well, A4 certainly has a subgroup of size 12. What is it?
Identity. But yeah, the identity. If it was to background.
Yeah. So all of it.
Oh yeah. Oh yeah.
Everything. Mm. Yeah. It certainly has a subgroup of size 1.
Yeah.
The identity. Yeah. The trivial subgroup consisting of just the identity. It's the most boring group in the world. Just as the identity that sits there and multiplies itself. It's the same thing as itself. Nothing ever happens. Okay. So it's got groups of size 1 and 12. Does it have a group of size 2? Give me a subgroup of size 2. So size 1, the subgroup is the identity. Size 12, the subgroup is all of A4. Size 2, well, it must contain the identity and one other thing.
6.
What I heard there was a number. What I should have heard was a certain permutation. The elements of these things are permutations, aren't they? So give me a permutation, and it has to be an even permutation, it has to come from A4, which has order 2. So we want to write down some permutation there, but I want the group to have size 2, so I want that to be all that's in it. So if you take that permutation and square it, it better be the identity.
The inverse permutation?
Inverse of what?
Sigma.
What sigma?
Oh, is that 4?
No.
No, because I was thinking 4 squared is 16, but then obviously circle on 12, you go back to 4.
Yeah, but you think of numbers, like I'm looking for permutations of 4 elements.
Is there more than one subgroup size too?
Yeah.
Because it could be any two elements. Because if it's square, it's still got back.
Yeah, so all you need to do is name me an element of order 2 within A4. So I mean, the natural thing we think of being an element of order 2 is a 2 cycle. Let's say 1, 2. That's order 2. But it's not in A4, so it's an odd permutation because it's 1 transposition. Can you build something, an even permutation of order 2, using this idea that transposition is naturally the course of order 2? So any product of 2 disjoint transpositions. Okay? So this is the product, it's a permutation, represented here in its product as a product of disjoint cycles, which is the best way to write down permutations after all. It's the product of these 2 disjoint transpositions. So what happens when you square this permutation? It goes back to, yeah, being the identity. So square it, you've got 1, 2, 3, 4, 1, 2, 3, 4. But because they're disjoint cycles, they commute. So all the 1, 2 can go beside the 1, 2. And you got 1, 2 squared, that's the identity. It's 2 cycle transposition. And you got 3, 4 squared. But that's the identity. So there is a subgroup of size 2. Subgroup of size 3. Well, it's got to contain the identity. So keep it simple. Which kinds of permutations have order 3? Any 3 cycle. Yeah, when you square this, you get 1, 3, 2. When you cube it, it's a 3 cycle, it's the identity. Yeah. Remember, this is the 1, 2, 3 is the permutation, which sends 1 to 2, 2 to 3, 3 back to 1. So when you square it, 1 goes to 3, 2 goes to 1, 3 goes to 2. That's that one. But when you cube it, 1 goes to 1, 2 goes to 2, 3 goes to 3. So when you cube it, you get the identity permutation. So that would generate your subgroup of size 3. So yes, there are subgroups. Subgroup size 4. Oh, and of course, 3 cycles are even. Remember, a cycle with an odd number of elements is an even cycle. Use the terms. Because the 1, 3, 2 is a product of 2 transpositions, 3, 2, and 2, 1, isn't it? No. 1 goes to 3, 3 goes to 2, 2 goes to 3, 3 goes to 1. Yeah. So it's a product of those two transpositions, the even number of transpositions. And subgroup size 4. I'm unsure a little bit. Doesn't spring to mind, so foursome. Okay, just brought to mind. But I mean, what's a natural element of? Oh no, sorry. No, I was thinking of a 4 cycle, but a 4 cycle is not. So it won't be an A4. So I'm not sure about that. But the one that's laid out in the book, anyway, because that's what I wanted. So I'm unsure about that. Maybe it does have a subgroup of size 4, maybe it doesn't. Think about that. But what we can prove, and what is proved in the book, is that it doesn't have a subgroup of size 6. Okay? Size 6 can't have it. It's proof by contradiction. Assume H is a subgroup of A4 of size 6. Which remember is half of the size of A4. So in our coset picture, here's A4. Here's a subgroup of half the size. How many left cosets are there? The subgroup itself is one of the left cosets. And all cosets, yeah, have the same number of votes. So there's only room for one more coset. Okay. So we have H itself and one other coset. And therefore, oh yeah, also, so only two left cosets, and also only 2 right cosets. We haven't mentioned right cosets much. But you know, you can play the game with right cosets just the same way as you can play the game with left cosets. Right cosets, remember, is where you multiplied all the elements in H on the right by an element in G. So and H itself is always a left coset. It's the left coset represents with the identity. It's also always a right coset. Okay. So the other coset is just the complement of H in A4. And it's the other left coset, it's also the other right coset. So we can actually say for all elements G from A4, the left coset represented by little g is always the same as the right coset. Okay. It comes from the subgroup H. G comes from the subgroup H, then GH would be equal to H. It would be equal to HG. If it's one of the elements from outside H, complement of H, then this will be true as well. The left coset, it won't be H, it will be this other set. And the right coset as well, it can't be H if the element is from outside of H. So it must be that other half of A4 as well. Or in other words, this is equivalent to saying that GHG inverse is always equal to H. Okay? By GHG inverse, well, you've met that before. That was in one of the exercises. It's the conjugate of a subgroup H by an element G. Sorry, H now. H. So I just multiplied both sides on the right by g inverse. So the way we get the contradiction, the way we prove that this H can't exist, is we ask ourselves, where are the 3 cycles? Well, A4 contains 8 3 cycles. Maybe list them. There's 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2. They're all the ones with 1 in the first position, aren't they? They're all the ones that feature a 1. So the ones without a 1, well, we got 2, 3, 4, 2, 4, 3. And those are 2 other ones. Which other ones haven't I listed yet?
4 and 3, 3 and 4.
Sorry?
1, 4, 3, 1, 3, 4.
Yeah, the one, yeah, the 1, 4, 3, 1, 3, 4. Okay. So those are all of the 8 3 cycles within A4. Where are they in this picture? What remarks can we make about that? How much space is there in this picture? There's only A4 is size 12. H we're assuming is half of A4, so there's 6 elements here. So there must be 6 elements here as well. So where are these H 3 cycles? What can we say about the distribution of the H 3 cycles?
These automatically assume that 4 goes into each, and that there's 2 missing on either side. But is that due to the 6 not being able to be represented, as you said, that it can't happen? Because we had another cycle group, it would create 2 more.
Well, you're onto the right idea. I mean, there's 12 elements in the whole thing, so there's enough space in the whole picture for the 8 3 cycles.
That's as far as
I don't think you quite landed on the, but you're hovering around the, no, use the sensible stuff. So where are they? What can we say about it? I mean, obviously, I don't know where this one is. Where is this one? Well, it could be here, it could be there. I don't know. I'm just supposing there is a subgroup H of size 6. But what can we say for definite about the distribution of it?
That every every odd one that you lifted, the 1, the 3, the 5, and the 7 are on the left, and the even ones are on the right.
How do you know?
Because the inverse exists on either side.
No, like if something's in H, its inverse must also be in H.
Oh yeah.
So it's a subgroup.
The 1, 2, 3, and the inverse of 1, 2, 3 always have to be on the same side.
Yeah. Which side though?
Whatever side they're all.
Whatever side they're on.
But at least, well, if there's 8 in total, one of them is guaranteed to be in either set, whichever way you look at it, because there can only be a maximum of 6 in one.
Yeah. So yeah, we can't say anything specific about this one or this one or this one, really. Other than, if it's partnered with its inverse, it must be in the same side, because it's a subgroup. But yeah, what we can say is that, well, there's 8 things here, but there's space, total space 6 here, total space 6 here. So there must be one of the 8 in here, at least one. There must be some of them in here and some of them in here. They can't all squeeze into one half and avoid one of the cosines. So that's the trick. So therefore, H contains at least one 3 cycle. Now, for the sake of argument, we may as well say it contains this one, 1, 2, 3. Once we know that it contains one of them, if it didn't contain 1, 2, 3, we could relabel the number. Remember, these numbers, they're just being used as distinct labels. So, what does that mean again? You've seen that before? WLOG? Have you? Means without loss of generality. It looks like we're making a specific choice, but we're not really. We without loss of generality, can assume 1, 2, 3 is in H. Of course, as you remarked about inverses, therefore 1, 3, 2 is also an element of H. H is a subgroup. And then he just keeps riffing with this, using this intermediate fact we got up here. And because you start to see that if you do, so I'm just copying out of the book here, 1, 2, 4, 1, 2, 3, 1, 2, 4 inverse, this must be in H by this result up here. Okay, because it's a G inverse. And that is, of course, 1, 2, 4, 1, 2, 3. And the inverse of 1, 2, 4 is 1, 4, 2. When you actually work that out, that's the 3 cycle 2, 4, 3. So that must also be in H. But then its inverse, which is 2, 3, 4, that must be in H. How many things have we got so far? We've got 1, 2, 3, 4. We keep going. I think we can find another 2. So this other triple product we looked at is 2, 4, 3, 1, 2, 3, 2, 4, 3 inverse, which is 2, 4, 3, 1, 2, 3, 2, 3, 4, and that's one of the other ones, 1, 4, 2. That must be in H. But that implies its inverse, which is 1, 2, 4, is in H. H is a subgroup. It must contain inverses of all its elements. So 1, 2, 3, 4, 5, 6. Suddenly I've listed down 6 elements that have to be in H. Of course, H was supposed to be a subgroup. It must also contain the identity. So suddenly we're forced to the conclusion that H contains 1, 2, 3, 4, 5, 6, 7 elements. Which is a contradiction, because we assumed above assume it's a subgroup of size 6.
On both sides. Yeah.
We're assuming it's a subgroup of size 6. We're suddenly forced to the conclusion it has 7 things, and that's a contradiction. So H contains at least 7 elements. Worry for a minute that we found a contradiction in the fabric of reality. A 6-element thing containing 7 elements, but we say no, it's not that exciting. It's just that the thing can't exist. Okay, so we've ruled out the possibility of a 6-element subgroup in A4. So A4 has no subgroup of size 6. So I think that's the easiest group to show that it definitely doesn't have a subgroup of size on the device as a group. So that's why it's the kind of standard example that's rolled out. You can actually do it for a whole host. The coursework last year, we got them to repeat this kind of argument in some of the other alternative groups, say 5, 6, and 7, and so on, with the help of Sage and so on. And probably get you guys to do something different this year. but it's a nice argument. So you notice this argument, we're down in the dirt with A4, looking, doing calculations with the elements of A4. Whereas the proof of Lagrange's theorem was much more up there, much more abstract, just talking about groups in general. So this is specific calculations of a specific group. The proof of Lagrange's theorem was just general theoretical argument about all finite groups. Okay, I'm sorry, I mentioned to George earlier that I might say a bit about some of the exercises when we were talking. I did say a bit about it to him. But, so sorry, I only had a bit of time, I didn't have time to do these. But on Friday, the lab session, there isn't a huge amount on SAGE. In fact, most of the SAGE exercises here is mostly about doing calculations with the number theory stuff in the group of multiplicative congruence classes, which you're kind of familiar with from number theory. So we can do a little bit of that, but maybe on Friday we can concentrate on some of the exercises I might take you through or help you out, give you some tips on 6. 6 was the harder one of all those, but we'll maybe look at some of the other exercises as well in the lab on Friday. Okay. So do read through the chapter. I've covered the most important parts of the arguments there. Didn't spend a huge amount of time on examples, of course. But read through the examples there, read through the proofs, and yeah, I'll see you on Friday. We'll do examples.